So the next question is, how do we solve a planning problem now that we know how to represent it in PDDL? And the answer is, like many answers in this course, by state space search. And the state space search here comes in two flavors. We have a progression search and we have a regression search. And we'll also see how to generate heuristics for our search. And the advantage with PDDL is that the heuristics can be generated automatically. So let's start with the progression search. This is also called forward search. We start with the initial state and we apply each possible action repeatedly, hoping to find a goal state. So we unify elements of state with preconditions to find applicable actions, and then we use the effects to construct the successor state. Remember, we said each action has a delete list and an add list, and the delete list is made up of the negative literals and the actions effect, while the add list is made up of the positive literals and the actions effect. So we build successor states by removing the literals in the delete list and adding those in the add list to our state. So let's take a look at an example. Here's our initial state for the cargo problem. We have to basically find every applicable action. So fly P1 SFO is an applicable action here. We construct the successor state from there, and we consider fly P2 JFK SFO because that's also an applicable action. And we consider load C1 P1 SFO. That's also an applicable action. Or load C2 P2 JFK. All of these are applicable actions. And we keep building our search tree by applying actions and computing successor states. And we are hoping that one of our states, one of our successor states, will be a goal state, will entail the goal. So we may have to do that for a while. And the problem here with this search is that we are really exploring some irrelevant actions. So if our goal is to get cargo to JFK, we should really not fly any planes before loading the cargo. So many of the actions in our search tree are irrelevant to our search. So the only action here that's going to get us to our goal is to load C1 on P1 at SFO. Let's take a look at another example. Let's say that our goal is to own the AI textbook. So a textbook is identified by an ISBN number. And in our initial state, we have ISBN numbers for many textbooks that are available for sale. So we have a buy action schema that we can express in terms of precondition. We buy I if I is ISBN, and as a result, we own I. So if we were to start from our initial state and perform a progression search, how many applicable actions do we have? And the answer is we would have billions of applicable actions because ISBNs are 10 or 13 digits long. So this action schema has at least 10 billion ground actions. That's a huge branching factor for our search tree. And if we are conducting an uninformed forward search, we'll have to enumerate them all and we'll be doing that for a long time. So progression state space search is only feasible when we have strong heuristics. PDDL representation makes it really easy to automatically generate domain-independent heuristics. Let's take a look at regression search. So with regression search, we start from the goal and search backward until we reach a state implied by the initial state. Note that the goal does not represent a single state, but rather a family of states. So to navigate from the goal to a predecessor state, we unify elements of a state with effects of actions to find relevant actions. We use the preconditions to construct previous states. So we remove the add list from the current state and add the precondition to obtain the predecessor state. So here's what that looks like for our cargo problem. Let's say our goal is to have C1 at JFK and C2 at SFO. We look for relevant actions here. So for an action to be relevant, one of its effects must unify with an element of the goal. So let's take a look at our unload action. One of its effects at CA unifies with at C1 JFK. So the unload action at C1P JFK is now a relevant action. We can also say that at CA unifies with at C2 SFO, and we get the relevant action unload C2P SFO. And we build our tree backwards here, right? So we keep constructing predecessor states and going back. So here we find that the load C1 PJFK action is relevant because its effect in CP unifies within C1P, which is an element in this state here. And then we can also find that the fly action is relevant because at P2 unifies with at P JFK. Now, what do we get when we apply regression search to our book buying problem? So our goal is to own this book, and there's only one relevant action. So that's the relevant action. We construct the predecessor state, and this state is actually implied by the initial state. So one of the advantages of the PDDL representation is that it makes it easy to automatically generate heuristics. So if you remember, heuristics are exact solutions to a relaxed problem. Now in PDDL, there are different ways to relax the problem. We could increase the number of possible actions. We can ignore the preconditions completely or ignore negative effects. We can also reduce the number of states. We can merge multiple states into one. And finally, we can decompose the problem into two or more easier problems. So let's see how to do that next. Action schemas have preconditions. What happens when we remove preconditions from action schemas? All actions become applicable. So let's go back to our sliding puzzle and write an action schema for the slide action. We'll use the predicates on, blank, and adjacent. Take a minute and write the preconditions and the effect for the slide action. We need to have the tile on S1. We need to have S2 blank, and S1 must be adjacent to S2. The effect is that we'll have T on S2, S1 will be blank, T will no longer be on S1, and S2 will no longer be blank. So what happens if we remove the preconditions? All the actions become applicable. We can slide the tiles anywhere, and we get our number of misplaced tiles heuristic. Now, instead of ignoring all the preconditions, we can choose to remove selected preconditions from the action schemas. So going back to our sliding puzzle, instead of removing all the preconditions, we can simply remove the blank S2 precondition. So what do we get if we do that? If we ignore the blank S2 precondition, we get our Manhattan distance heuristic. We can also ignore negative effects of actions. So, no action may undo the effects of another. We get a monotonic progression toward the goal if we do that. And this is known as the ignore delete list heuristic. We then use hill climbing to find a solution, and the cost of that solution is our heuristic. To reduce the number of states, we map several ground states into one abstraction. We do that by ignoring some literals. For example, in our cargo problem, if our goal involves C1, C2, SFO, and JFK only, we can ignore all affluents that do not involve C1, C2, SFO, and JFK. And finally, we can use decomposition. We divide the problem into subproblems. So we solve each subproblem independently, and then we combine the solutions. So let's say that our goal is to get C1 to JFK and C2 to SFO. We decompose the problem into two problems, get C1 to JFK, and then get C2 to SFO. Now, there is this assumption that we would be making, and that's that the cost of solving a conjunction of sub-goals is approximated by the sum of the costs of solving each sub-goal independently. That assumption is optimistic where subplans interact negatively, but it's pessimistic when we have redundant actions in subplans that can be replaced by a single action in the merge plan. So consider the problem where C3 and C4 are initially at SFO. Now, if our goal is to get them both to JFK, when we decompose the problem into two separate problems, we are really overestimating the cost. What we should do here is we should use the maximum of the costs instead of the sum, because we can get C3 and C4 on the same plane and get them to JFK. There's no need to get each one of them on a separate plane. All right, so I want to leave you now with this monkey and banana problem. If we were in the classroom doing this class in person, we would be solving it together. I would have put you in teams and you would have worked on this problem together. But I'm going to still present the problem to you and hope that you'll work on it on your own. So here's our problem. We have a monkey in a room with bananas hanging from the ceiling. There's a box in the room, and the monkey can climb on the box to reach the bananas. Initially, the monkey is at location A, the bananas are at location B, and the box is at location C. So A, B, C are locations. They are independent of height. So the monkey and the box are at height low, and the bananas are at height high. If the monkey climbs on the box, he will be at height high. So in our initial state, we know that the monkey is at location A. We know that the bananas are at location B and the box at location C. The monkey is at height low, the box is low, and the bananas are high. The box is pushable, the box is climbable, and A, B, and C are all locations. So our goal is for the monkey to have the banana. So we write our goal as have monkey bananas. Now, I'm asking you to write the planning domain for this problem. So you need to write action schemas for the go action, the push action, the climb up action, the climb down action, the grasp action, ungrasp action, and the solution will be a sequence of actions from the initial state to a state that entails a goal. So just a few reminders as you work through this problem. In the state representation, whatever is not explicitly stated is assumed to be false, and an action schema has to include precondition, effect, and any variable in the effect of an action schema must appear in the action's preconditions. And the predicates we're using here are the at predicate, on, height, have, pushable, climbable, and location. And the constants are monkey, bananas, box, A, B, C, high, and low. So give it a try. And if you have questions about this, we can discuss it in the Q&A session.